So I'm Tarik Kaced. I come from Chinese University of Hong Kong. So I'm actually a postdoc there, and I'm finishing my postdoc. So if you have a job for me, I'm open. So after this shameless self-test plug, so I'm going to talk about how to apply conditional inequality to get bounds for the big covering number. And in turn, it will have applications to, for instance, communication complexity, or even to some more general graph theoretic problems. Okay, so how does it work? I first want to say that you use conditional inequalities every day. For instance, this inequality is just Shannon perfect secret theorem, and is actually a conditional inequality. Also, when you have linear random variables, you have Ingleton inequality, but only when your random variables are linear. So it means it's a conditional inequality too. So we have some other conditional inequalities that are non-trivial in some sense. I don't want to explain the details, but so far there's no application for them. And now in this work we're trying to generalize these inequalities and to show how we can actually get finally some application of non-Shannon type inequalities. So first, let's look at the conditions. What are the conditions? We are conditional inequalities, so there is some condition that must hold. So usually, conditions are just some terms, some information terms that are exactly zero. But these conditions are kind of fragile. So what we are trying to do is to relax this condition. But first, let's have a look at what this condition means. For instance, whenever x and y are independent, we can look at the graph where here you have all possible values for x, all possible values for y, and then there's an edge whenever x and y are compatible together. Compatible just means that the probability of x and y is positive. So when x and y are independent, it means that in this bimetric graph, we have actually all possible edges. So, and now, what's kind of interesting is that when we add a condition A, let's just look at A as a color, the color of an edge. So it means that for each possible color, we have a bimetric graph that is complete. So we call this a bicyclic. So if for all possible color we have a bicyclic, it means actually for this graph, this explains this condition. This graph is we have actually a bicyclic covering of a graph. Good. So what can we do with this? So what we will do is actually show that. Okay. So now for the theory, we prove some unconditional inequalities that in turn would imply some more generalized conditional inequality here later. So first, what I want to say is that these inequalities are actually laws of information, but they are non-linear in some sense. So, okay. Then when we add some new combinatorial constraints that are also constraints for graphs, then we can show that in this lemma, some terms equal to zero. So we can show that these kind of terms that are not really pleasant to the eye, they actually become zero. So this is a good thing. It means that as a theorem we have two new inequalities that actually are a generalization of these ones, of the non-trivial conditional inequalities here. And the good thing is that now we will see that we can apply these inequalities, just because now the condition has somehow relaxed, and it allows us to find some application. What's the application? The application will be on the size of a bicyclic covering. So let's go here. This is the first example of application. So remember, the bicyclic covering number is just the minimum number of complete bimetric graph needed to cover a graph, any graph G. So, okay, now suppose you have a graph, and I want to say that you can induce probability distribution on this graph, and it will create magically some random variables. For instance, how to do this? You just take an edge at random, and then it gives a distribution for x, y, and a, where x is just the left-hand side of the edge, y is the right-hand side of the edge, and a is the color. Let's say the color of the edge. So for a particular graph that we call JKN, which is just a bimetric graph. Okay, let me try to explain it. It's a bimetric graph where on the right and left-hand side we have all possible k element sets from a set of 1 to n. And there's an edge between x and y whenever x and y are disjoint. So for those who are familiar with this, it's actually a graph related to the k disjointness communication problem. So what we're going to have in the end is a bound for the communication complexity of the k disjointness problem. So how do we do this? First, we notice that for this graph and for this random variable x, y, a, we have that this inequality is violated. So this term is actually really bigger than this term. What does that help? It helps because now we will create a new random variable z. Z is just, okay, you have your graph. You take an edge, x and y, and this edge actually belongs to a big-click. So which big-click do you take? You just take a big-click at random. So you define z as, whenever you know x and y, you define z as a random big-click containing x and y. Okay, now, magically when you do this, you can actually apply one of our conditional inequality that we just explained. And when you apply it, when you look here, you see that you take this inequality, this which is not an inequality, you add z everywhere, z which is just the index of the big-click, and you get that this is actually an inequality, just because of our new conditional inequality. How does this help? Well, the difference between these two is that you have z everywhere in the condition. So it implies a bound on the entropy of z. Remember that z is just the index of a big-click. So in the end, you get a bound on the entropy of the big-click, so a bound of the number of big-clicks needed in this big-click covering. So in the end, wrapping up, you just get a bound for the communication complexity of the k disjointness problem, because you just have a bound on the big-click covering number. There's also some other application for partition. If you want to partition a graph into k matchings, and you want your partition that it satisfies a particular condition. The particular condition is kind of weird. It just says that for each particular matchings, whenever you have an edge x and y, then you cannot reuse x and y in other matchings. So if you cannot reuse, it just means that the number of matching that you need will be kind of big. How big? It's actually difficult to say. But if we use this inequality, you can actually have a bound actually on how big the number of matching must be, and you have this nice theorem that, okay, if you have such a kind of matching, then the number of matchings you need should be bigger than the degree of the maximum degree of the left-hand side and times the degree of the right-hand side. And this corollary looks kind of a simple combinatorial problem. However, I don't know how to prove it without entropy. And somehow, I think that the entropy argument looks cleaner. Okay, so I think this is all I have to say for this big-click covering thing. If you want more details, we have an archive paper, exactly this one. So I think that's it. Thank you.